Thanks, Michael. Thanks for inviting me, and it's a nice introduction. Today, previously, my talk was neutrino CP measurement, but I thought probably it's a little bit misleading. Actually, I'm doing a theoretical study, so I changed to the current title, neutrino CP phase and the new physics. So my talk would divide into three major parts. First, introduces the leptonic CP variation, especially why it's so important, and the current status of CP measurement, especially the accelerator experiments T2K, NOvA, and how to improve the CP measurement with low energy neutrinos from muon decay at rest. And finally, about these new physics that can enter into CP measurement, especially those can fake the CP effect, and the possible ways of identifying these new physics to guarantee the CP measurement. So the first part, I like this book by Judge Raffet very much, especially there is one sentence in his introduction or somewhere. He mentions that neutrino actually has almost minimal properties, almost zero mass, zero charge, zero dipole moments, and almost zero decay rates, zero almost everything. But still, we know that neutrino is a very, very important topic in particle physics. It's the first new physics beyond the standard model, especially the neutrino mixing and the oscillation phenomena. So the basic picture of neutrino oscillation is we have three generations, three neutrinos. So these three neutrinos, we label them according to the associated leptons, the electron flavor, muon flavor, and the tau flavor. These three neutrinos, they only differ by mass. Everything else is the same. So they can mix up from their mass matrix. And then we need to diagonalize the mass matrix to get a definite mass. And only for the mass eigenstate, they are physical. They can have this definite dispersion ratio, and they can evolve as mass eigenstate as a plane wave. And between the flavor state and the mass eigenstate, the connection is this PMNS matrix. It is a 3x3 unitary mixing matrix. It contains three mixing angles. Here I use notation that's different from the literature. Usually people use 1, 2, 2, 3, and 1, 3. It's kind of like a three-dimensional rotation. But I named them according to their physical meanings. So C.13 is first measured in reactor experiment. So I use R to indicate its physical meaning. And 1, 2 is measured from the solar neutrino oscillation. That's S, and A is atmospheric. And you can see that in addition to these three mixing angles, we also have one Dirac CP phase, delta T, in the mixing matrix. And these four parameters can appear in the neutrino oscillation. In addition to these four, we can have another 5 degrees of freedom. One is on the left-hand side in this P, which is the diagonal refacing matrix, 5, 1, 5, 2, 5, 3. These are unphysical. We cannot measure it. And another 2 associated with the mass eigenstate, delta M1, delta M3. These are actually the Marlon CP phases. So in total, we have 9 degrees of freedom in a 3x3 unitary matrix. So this mixing feature would lead to the neutrino oscillation, which is a microscopic quantum interference phenomena. As I mentioned, only mass eigenstates can develop, can evolve as plane wave with definite evolution phase. But with different mass, the evolution phase is different. So you can imagine there are 3 different phases. But when we measure them, we have to use the flavor eigenstate because neutrino is neutral. We cannot directly see. What we can see is the charged leptons. So we always detect neutrinos in flavor eigenstate. And then these would cause some interference among the 3 different evolution phases. And these macroscopic quantum phenomena can happen over a distance like up to thousands of kilometers. And I use these 2 neutrino mixing to illustrate the basic idea. So oscillation probability is a function of the mixing angle theta. This is just a 2x2 mixing. So there is only one mixing angle. And there is one mass square difference, indicate the difference between the two mass eigenstates. These two, one determines the oscillation amplitude, another one determines the frequency. And then we use the measurement. Once we get these patterns, once we get the amplitude and frequency, then we can infer the mixing angles and the mass square difference. And that's exactly what we have done for neutrino experiments. Of course, in the reality, it's not just two neutrino oscillation, it's three neutrino oscillation. So we have three mixing angles and two mass square difference. So currently, from the global field of all neutrino oscillation experiments, we have measured the three mixing angles. Theta 1, 2 is around 33 degrees. Theta 2, 3, that's 42, and theta 1, 3 around 8 degrees. And theta 1, 3 is measured by Dirac. And actually, theta 1, 3 is the first entering the precision era. And in the future, we also have Juno that can measure these mixing angles down to sub-percentage level. And we currently have also measured the mass square differences. You can see that these mass square differences are very, very tiny. One is 10 to minus 5 electron volt square. Another one is 10 to minus 3. Of course, we can also measure CP phase. Currently, there is some constraint on this value, but not fixed yet. So since we can see that neutrino mass is very, very small. And currently from cosmology, we can also indicate its absolute value is below electron volt scale. And then the question is, we need to understand why neutrino mixing is so important, especially its mass is negligibly small if you compare with the HV. So for this mass, it wouldn't affect that much thing, especially for Higgs boson. It can explain the mass of all those standard model particles. And not to say we have this QSD and chiral symmetry breaking that explains the majority of the mass in our universe. Like proton, most of the mass are not the quark mass. Actually, it comes from interaction. But still, we emphasize neutrino a lot. The reason is it's related to the matter-antimatter asymmetry. And things changed a lot in 2012, 12 years ago, especially after this Dirac. In that year, they announced the measurement of non-zero theta 1, 3 on March 8th. And also, it's very interesting to observe that in the same year, HG observed the standard model Higgs boson, and its mass is 125 GeV. And this thing played together to put neutrino CP very important, because with this mass of Higgs boson, it's impossible to have first order phase transition. And then from the quark sector, that quark CP is not enough to explain the matter-antimatter asymmetry in our universe. Unless we introduce other degrees of freedom, other scalars. And the alternative way is the lepton genesis, using the CP phase related to neutrino. Of course, we also need to add extra field, especially the right-hand neutrino, for example. But this one has a much stronger motivation, because it's motivated one thing by the ground unification theory from SL10 models. And also, this right-hand neutrino is a necessary ingredient for type 1 seesaw to expand the tiny neutrino mass. And the same heavy right-hand neutrino can have decay into two different channels. One is into the lepton channel, another one is anti-lepton. And since these are two different processes, then it's possible to allow some difference among their decay widths from this CP variation. So if there, here I just illustrated the idea. I put this Dirac CP phase and the Morana CP phase here, but of course it involves much more. But mostly importantly, we need to at least see something at low energy for the CP variation. Then we would be more confident about this lepton genesis mechanism for expanding the matter-antimatter asymmetry in our universe. So although this neutrino mass is very tiny, but we first need to have this mixing, especially 3 neutrino mixing and 3 non-zero CP phases, mixing angles. Then we can have the Dirac CP phase in the neutrino sector. Then we can, in principle, see some indication of high energy theory. That's the reason why CP is so important. So after 2012, the neutrino experiment, in my understanding, the most important topic is CP. Although there are several other things we need to measure to precisely fix, for example, CDAW 2-3 and also the mass hierarchy. But CP is of ultimate importance. And currently, we already get some indication for this CP phase value. For example, from T2K, roughly 4 years ago, T2K published this preliminary result to show there is roughly a 3 sigma confidence level indication of non-zero CP. They exclude half of the parameter space, and they get some best fit value that's close to -90. And this is a good sign. If it's really true, that means not just in the quark sector, but also in the leptonic sectors, CP phase is maximal. And the experiment has been going on. In addition to T2K, there is NOvA in US. NOvA has high energy. It's doing independent measurement. And recently, they have this joint analysis, T2K plus NOvA. And the result shows that for this both mass ordering case, you can see that the best fit is still around maximal CP, -90 degree. Of course, we can see the separate analysis for normal and inverted. So we still need to keep measuring this CP phase, but currently, I think we already at one stage to think about for the future. Suppose we keep improving this at some point we exclude the CP conserving delta CP equals 0, exclude this case, then what's the next? So excluding non-zero value means we actually first discover some non-zero CP in the leptonic sector, but we still need to get a precise value for the for excluding model, for examining model, or for other purpose. So that's why I want to do a phonological study of this neutrino CP phase. Then it comes to the second part of my talk. How this accelerator experiment measures CP, and what's the shortcomings, and how to improve this CP measurement. Well, before going into the details, I would like to mention that the accelerator neutrino experiments actually was invented in 1960, and T. Lili and C.N. Yang actually involved a lot in the process. This is kind of like ignored by many people. Everybody say they actually worked on priority variation, but actually after priority variation, they also helped to develop this high energy neutrino beam as a tool to probe weak interaction. Together with Schwartz, they published back-to-back papers. One is on experimental side, another one on the theoretical side. So if we want to know details, actually, I wrote about a small piece to summarize this history. Well, the basic idea of accelerator experiment is we first use a proton to accelerate the proton to hit the target. And during this process, it can produce a lot of pion. And these pions, they would decay to muon. And it can already produce one neutrino. So pion to muon is two-body decay. So one neutrino, one muon. This muon can further decay into electron or positron plus 2 neutrinos. So this chain of reaction can produce 3 neutrinos. And that's the basic idea for all accelerator neutrino experiments. For example, for these T2K in Japan, The source JPAC is on the east shore of Japan at Tokai village. And these neutrino, once they are produced, they would just keep moving towards the detector, Kamioka, on the west shore of Japan. And for NOVA, it's similar. The source is at Fermilab, and the NOVA detector is in north in Minnesota. This experiment, since when it's produced during the production, the pions are charged pions, pi plus, pi minus, and also for muon, they are charged particles. So actually, we can use the magnetic field to control its direction. So we can select whether it's neutrino or anti-neutrino. So usually the experiment can do both modes. So the reason of before going to the mechanism, let me mention a little bit. In future, actually, T2K would get upgraded. First, the flux would be higher. T2K2, currently, I think they already finished upgrading. And also for NOVA and for detector, Super K would change to a much larger version, Hyper K. And also, it's possible to port another detector between Japan and Korea. That's T2KK. One is Kamioka, another one is Korea. And also T2KO. T2KO is the island between Japan and Korea. So that's the Oki Island. And also in China, people are discussing about this moment using accelerator to produce neutrinos, but the detector probably is Super K. This is not fixed yet. People are still thinking about it. And also using some accelerator to generate the neutrinos as a byproduct of the quite experiment. And also for atmospheric neutrino, it's also possible to have very high energy neutrinos that can also be used to measure the CP phase. So a lot of designs, the basic idea is still the same. First, use the proton beam to get target to produce pion decay to muon, and muon decay to get neutrinos. So we can use quite unified way to describe the basic process. So this experiment needs to measure both neutrino and anti-neutrino modes. The reason is in the oscillation probability, actually we can have both cosine and sine terms. In a general case, we have both of them. If we have both modes, then it's possible to have the difference among them. So this is in the vacuum, oscillation in the vacuum. So I made this simplification. Then for vacuum oscillation, the difference between these two is proportional to sine. And this can be uniquely used to fix the Dirac CP phase. And in order to maximize the oscillation probability, usually the experiments are put at the first oscillation peak. That phi 3 that's the oscillation phase, which is proportional to the mass square difference. That would be at maximal oscillation, that's pi over 2. And then for this alpha 2 that's proportional to the smaller mass square difference would be suppressed by a factor of like 3%. So since the CP effect actually is not just proportional to sine delta D, but also this alpha. So this oscillation from muon flavor to electron flavor, its size is not that large for CP measurement. And so we needed to get a very precise measurement of this oscillation process. But this has multiple issues. If we take a look at this more detailedly, first we need both neutrino and anti-neutrino modes. And the interaction cross-section is typically larger for the neutrino mode. So sigma nu is larger than sigma nu bar. So that means in order to get a comparable event rate, we need to assign most of the beam time to the anti-neutrino mode. For example, it's 2 over 2 to 1, this kind of thing. Then this would undercut the statistics. The event rate wouldn't be that large. And with the smaller event rate, the statistical uncertainty would be large. So the efficiency is not that high. Although we run, for example, 3 days, but 2 days are assigned for anti-neutrino, and anti-neutrino mode not including the production and the detection part, the cross-section is smaller, typically smaller. And another thing is for the degeneracy, since we can only measure this sign delta D at the first oscillation peak, then from when inferring the value of CP, there are two solutions. One is delta D, another one is pi minus delta D. There is some degeneracy between them. And another thing is CP uncertainty. Currently from T2K, it indicates that CP is around the maximum CP minus 90 degree. But with only a sign delta D dependence, you can imagine the coefficient, the derivative. The derivative is something cosine delta D from this sign. And cosine delta D is intrinsically small for maximal CP. Then the uncertainty would be large. Uncertainty would be large. That means we change this CP phase. It wouldn't change this oscillation probability that much. It's at kind of like a minimum, a flat minimum. So the uncertainty is intrinsically large for maximal CP. Although the indication of maximal CP at T2K is a good thing for discovery, for making discovery of non-zero CP, but it is not good for precision measurement. For example, in the future, if you want to know exactly what's the value of this CP phase, then we need to find a slightly different way. So these three intrinsic problems are kind of like a universal for T2K, NOvA. For this Dune is slightly better because it uses different beams. It's not just the sign dependence, but still it has efficiency problem. So we want to find a solution. And the solution is the low energy neutrino, muon decay at rest. The basic process is roughly the same. Proton beam hits target. But when pion decay, it's not a decay in vacuum. It's not a decay when it's still flying. If you put this target, a sick target, so when the proton beam injects into target, it would produce this pion inside the target, and the pion would stop there. Because these pions, they are charged. For this pi minus, since it's negative charged, it would be attracted by the positively charged nuclei. And then pi minus is absorbed. But for pi plus, it would lose its energy very quick due to this electromagnetic interaction. And then it would decay at rest. And during this process, it's just a two-body-defined state. So the neutrino, nu mu, is mono-energetic. Of course, mu plus is also mono-energetic. And the mu plus is also positive charge. So it would first stop and then decay at rest to produce E plus and nu mu bar and also nu E. And since it decays at rest, the final state particle spectrum is well known. For this neutrino, you can see that nu mu bar, it follows this red line. It's a wider spectrum, and the peak is around 50 MeV. So the upper limit is half of the muon mass. So that's 53 MeV. This spectrum is well predicted. And then these nu mu bar would travel in all directions. And during the process, they would oscillate to other flavors. And then a detector measuring nu mu bar from this oscillation can be used to measure that CP phase. Although it seems like it's roughly the same process as the accelerator neutrino experiment, but the feature is, first, it has much lower energy. The energy peak is around 50 or 45 after considering the resolution, the smearing effect. The peak will move to 45 MeV, but for accelerator, the peak is much higher. And that means in order to produce these mu neutrinos, actually we don't need to accelerate a proton to very, very high energy. We just need to produce like 800 MeV proton beam. But for T2K, that would be several GeV. So with the same electricity power, actually we can produce much more mu-dot neutrinos. Then for these mu-dot experiments, you can just focus on the anti-neutrino mode. And for the accelerator, it can focus on the neutrino mode. And this can significantly enhance the sensitivity, at least the event rate, and then reduce the statistical uncertainty. And the second thing is we can avoid the degeneracy issue. You can see on the left-hand side is the T2K. That's the coefficient for cosine and the sine delta terms. So you can see for the energy around 550 MeV, the red and the blue ones would vanish. That's the coefficient of cosine terms. Only sine would survive. And that's exactly the reason for degeneracy and also for large CP. But if you look at the muon decay at rest oscillation, if you put a detector around, for example, 30 kilometers, then we can see the blue and the purple lines, both of them can be sizable. Around 45 MeV, you can see no big difference. So both sine and cosine can survive. So with these assignments, actually, first, it can improve the statistics, improve the event rate. Second, it can remove these, to avoid only sine delta D dependence. It introduce the cosine term. And then these three issues are solved. So this design is, of course, there are other designs like Dirac. Dirac, they use a similar idea, but they have three different sources with only one detector. So that's the picture in the middle. The detector is here, and the three black box, there are three different sources. And as I mentioned, the neutrinos, once they are produced, they would just travel isotropically in all directions. Then actually we don't know where from that neutrino comes from which source. So different source has different baseline length, so different distance from the detector. And this distance actually is very important because in the oscillation, the oscillation phase is proportional to distance. So without knowing this distance, actually we cannot infer those oscillation parameters. So for Dirac, although they have three sources, actually they can only run at most and turn off the other two. So different sources would take shift. Then it's a huge waste, huge waste. For us, we just need one detector. For example, in Japan, people have already built Super K in Kamioka, and now people are constructing the Hyper K, which is just 8 kilometers south of the Super K detector. Then we put one source next to it, and then we can have two baselines simultaneously. The duty factor can be up to like almost 100 or 100%. That would be very, very much better. So one thing is less source, less expensive, and also it does not require that high intensity. So this technically is not that challenging.
So what baseline do you have from Hydra? So how close is the source from the detector?
Let me see if I have, I have plot on next pages. So
okay, good. I wait.
Kind of like a 10 kilometer, 10
okay.
or 18, depends. I will show you how to determine the baseline. And then, actually I should focus on this one. So one mu-dot source with the two detectors, 4 duty factor, almost a 4 duty factor. Of course, we need some maintenance time every year. And then lower intensity, and then cheaper and much easier. There are two places that we can do this experiment. One is the Kamioka site. Another one currently becomes impossible. That's before Juno experiment. People were still thinking whether we should use just a single detector or two detectors. If we use two detectors, then it's possible to put one mu-dot source and then use two baselines. But still, currently, people are still thinking about the possibility of CP measurement with dual detector. So coming to this baseline, roughly what we need is at the order of 10 to 30 kilometers, this range. So for T2K, the accelerator experiment, the neutrino travels from the east, from Tokai, to this chemical site. And the super K is in the north, it's smaller. For hyper K, it's roughly 8 kilometers south of it. It's much larger. Then, in order to maximize the event rate at super K, it's better to build this cyclotron complex in the north with distance, for example, 10 kilometers. So this is just the illustration, not the exact, the optimal baseline. And the optimal baseline can be seen here. We change the baseline and see what's the expected CP sensitivity. For different true CP phases. So we assume some true CP phase and try to generate a solid data and try to see what's the CP uncertainty from the fit. And it seems like around 18 kilometers, that's the optimal baseline. It can be as good as like 13 degree. And 13 degree is much better than the current T2K. As I showed earlier, currently they can explore the half of the parameter space, and people haven't started talking about the CP uncertainty yet, because that's roughly like 30 or around 40 between these two values. So that's a very rough measurement of the CP phase. But with this MUDA, in principle, we can approach 10 degree, approach it. And if you have a much larger T2K or T2HK, hyper K detector joining the effort, then it can reach something like 7 degree. And 7 degree currently we haven't fixed yet. It still spans from 0 to minus pi. That's 180 degree. But in future, if we can reach like 7 degree uncertainty, that will be very precise. Can help to identify can help to explore a lot of models. Of course, the disadvantage seems like a second detector, but as I mentioned, second detector already approved. So that's not something we need to worry about. It's just one source you can add. And this cyclotron can also be used for other purpose, for example, for material, for science, for biological science, those stuff. So that's the possibility in Japan. And recently we have also tried to think about the possibility with FrameLab. Actually, in 2018, I was visiting there, and I have started thinking about this. After that, people have proposed this SIA. SIA is a force detector in the dune site. So the dune, they still use the Fermi-Lab source and put the detector in South Dakota. So the distance is something like 1,300 kilometers. And the original design has 4 detectors, but it's very expensive. So people are thinking whether we should replace one detector by something different, for example, the SIA. The SIA detector, they use a water-based liquid scintillator. It works something like super K and hyper K, because hyper K is purely water. And this one uses water as the target material and scintillator to generate those light for detection. So once this came out, we found that it becomes possible again to have this MUDA experiment associated with accelerator experiment. So just add one MUDA source around the dune site, and together with the accelerator part, we can push that uncertainty also down to something like 7 degree. So these 2 major experimental sites, it's possible to make a further upgrade to get a better measurement of the CP phase. Okay, so that's basically my second part. since it has quite a large difference from the final part, maybe I should stop here. And if there is any question, yeah, please ask.
Can I ask another one? There is
Yes.
so in that table, so tune plus Thea, does that assume the full tune detector, or is that the stage 1 or the including?
Here we assume 3 detectors for Dune.
3 detectors. Okay, yeah.
Another one is CR. CR has 2 different versions, and one is just 25 kiloton. Another one is 100.
Okay, good. Thanks. And the difference between the left and right column, okay, that's depending on what's the real, or what's the CP phase. Okay.
Right. Yes. We just assume both are still possible. Just in case.
Yes, yeah. Makes sense. Okay, thanks.
Yeah, thanks for your question. And then I will talk about the new physics part. For this CP measurement, as I mentioned, it's very, very important. Once it's measured, I think people should consider seriously whether they should get a Nobel Prize or not. But in order to achieve that, we need to make sure what we measure is really the CP phase, just like something in the quark sector. And then it's better to exploit all possible new physics. And it turns out there are many possibilities. In the last several years, I've been working on this direction. Here, I just mentioned several topics that I have worked on, including non-standard interactions. For these non-standard interactions, actually, it has 3 types. One is a vector type, scalar type, and a bulk type, and also non-unitary mixing. And recently, I have been working on this ultra-rounding stuff. Since everyone is each topic is a big thing, so I just mentioned the rough idea. Why currently, in addition to how to say, make sure we measure CP phase, currently between T2K and NOvA, actually they are not fully consistent. If you take a look at their separate results carefully, you would see actually there is some tension between T2K and NOvA. On this plot, you can see T2K is square stuff. That's the best fit point. And for NOvA, it's this star. So they are not exactly the same. And for T2K best fit, actually it's at the region, in the region excluded by NOvA, although the confidence level is not so high. And for this inverted case, it's better. So roughly consistent, but still there is something different. How to explain it? These new physics are also being used to understand this tension, including this non-standard interaction, non-unitary mixing, also Lorentz variation and stem neutrinos. So first, these non-standard interactions. For neutrino oscillation, we use this vacuum Hamiltonian as the first order to describe it. So inside it, it has a mass square difference. And one common term has been removed because that one wouldn't change the oscillation behavior. And also on both sides, we have the mixing matrix. And this Hamiltonian is just the, how to say, the second order. The linear order is just the energy, E nu. And that one is also just one universal term. It wouldn't change the oscillation behavior. So we just throw it away. And for this second term, this linear term is suppressed by energy. When neutrino travels inside the matter, actually it would scatter with the material. And this can have some interaction, but there is one particular type, the forward scattering. That means neutrino does not change its momentum. So there is no momentum exchange. For this case, neutrino would feel some matter effect. And this effect actually, we are familiar with this consequence a lot. That's the speed of light in the material. For example, in crystal or in water, the speed of light is lower than its value in vacuum. The reason is the photon actually scatter with the material and experience the forward scattering. And this matter effect would lead to some effective mass for photon. That is called plasma mass in plasma physics. And this mass is the reason for the speed of light to be smaller. That's exactly the same thing. But for neutrino, it experiences the weak interaction. So in standard model, it would introduce the term VCC in the electron wave element, because in material we have only electron. That's the usual matter potential. But besides that, we can also introduce some extra interaction. For example, in some models, we have this C prime, and that one can induce forward scattering between neutrino and the material, and then it would introduce these epsilon parameters. So for the reason we don't need to care much. Finally, the thing appears in the oscillation is just these epsilon parameters. In principle, there are 9 different elements, but we have some symmetry, right? So we reduce some. For the diagonal ones, they are real. Off-diagonal ones, they are complex. So both can fake CP. Although the diagonal ones, they are real. There is no CP phase. But between neutrino and anti-neutrino mode, the matter effect would change the sign. And that's the faked CP effect. And so they are model-wise, it's not difficult to realize yet. For example, with this 10 MeV as C prime boson, with coupling 10 to minus 5, it's possible to generate large enough matter potential. And this one can significantly change the CP sensitivity. For example, at T2K, if there is no non-standard interaction, then it's the black line. So the largest chi-square value can reach something like 15. But if we introduce these non-standard interactions, depends on which element you introduce, the reduction is different. If we put all of them, then these would reduce by a factor of 5. The chi-square can only reach 3. So 3 is less than 2 sigma. That means although the T2K experiment can get very solid data, which I believe they can get it because they are experts, but our interpretation of the CP phase depends on our theoretical assumption. If we stick to just a 3x3 neutralization with the standard interaction, then it can reach this 15 chi-square. But if we introduce some new physics like non-standard interaction, then the sensitivity would significantly drop. So how could we trust the CP measurement? So that would be a very, very important issue to interpret the result. Then we need to wait even longer time to justify the result, to decide whether they should win the Nobel Prize or not. So to me, that's a very, very important issue. That's why I would spend so much time working on this phenomenological study. For this low energy muon neutrino, it can solve the issue because this matter potential, its effect actually is proportional to this energy. We can extract this 1/2e as a universal overall factor. Then this second term would be proportional to this neutrino energy. So it would have large enough effect for high energy neutrino beam. But for low energy neutrino beam, the effect would be negligible. And that's why we need a muon decay algorithm. For this muon experiment, you can see, although we can introduce non-standard interaction, but its effect is negligible. It wouldn't change the chi-square that much. And then we can combine these two. You can see that with this T2K plus muon, mu-sk is muon plus super K detector. T2K is the accelerator part. Mu-sk is the muon part. Then you can see that although it can still lead to some reduction, but the combination of these two would increase this chi-square from 15 to over 20. So that can actually guarantee the CP sensitivity. And then if we ask this T2K to purely run the neutrino mode, as I mentioned, it can focus on the neutrino mode, and the muon can focus on the anti-neutrino mode. then for these can even further increase. Of course, if we introduce all the elements, it's still around 20. But if some of them is not still, then it will be much, much better. So this is one advantage of this Muon experiment to distinguish these non-standard interaction to guarantee CP sensitivity. And for non-standard interaction, they're not just these vector type. People used to think there is only one type, the vector type. But actually there are a second type, the scalar one. For scalar one, just through the Yukawa coupling, then this matter vector would appear as mass. So although neutrino can have its genuine mass, but during the oscillation, it's not necessarily that the genuine mass that takes effect. It could be environmental mass. And it's a sum of them. So what we can see is combined effect. And since CP comes from the diagonalization of the mass matrix, this would fake the CP effect. And you can see that it changes the oscillation probability a lot. So in principle, we should also try to find a way to solve it. But here, actually, I would omit this part. For this, in addition, this dark matter can also scatter with a neutrino would scatter with dark matter, because it can couple with dark matter. For example, through this diagram, and you can see the neutrino momentum is still p. So initial one is p nu, the final state one is p nu. The momentum doesn't change, so it's still forward scattering. Dark matter is everywhere. So neutrino experiment, all neutrino experiments are done in the solar system. So it's in the dark medium. And this kind of forward scattering can also introduce effective neutrino mass. This is not neutrino, not like the scalar NSI. It appears as mass, directly as mass. For this dark NSI, it's forward scattering. This is a matter correction. It's inversely proportional to energy. And with this inverse proportionality, then we can see the correction would appear as effective mass. So that means actually the neutrino mass can be faked by interactions. Then, how could we be sure that there is neutrino mass? Actually, we don't know. For the scalar non-standard interaction, we can still say if we do the experiment in vacuum, then we can explore this scalar non-standard interaction. But for this dark NSI, dark matter is everywhere in the solar system. Then it's possible that the neutrino mass actually, the neutrino oscillation is induced by this dark mass, not by the genuine mass. Of course, it's possible to distinguish it. In my recent paper with Alexei Smirnov, we proposed to use the supernova neutrino. That's actually is very far away from us. It can cross the whole galaxy. And in the galaxy, the dark matter profile is different. And it can experience different mass. That leads to time delay effect. To use this way to distinguish it. But to me, the most important issue is still CP. This can fake the CP effect. And if you can distinguish it, then it can help to guarantee the CP sensitivity. So the first three are non-standard interactions. The fourth one is non-unitary mixing. Non-unitary mixing comes from the extension of the neutrino species. If we have not just three neutrinos, we can have extra like a stable neutrino, or even the one from the seesaw mechanism. They would mix with the active neutrinos. So that means the neutrino mixing matrix is no longer 3 by 3. So in the first 3 by 3 block, it's non-unitary. But for the oscillation, it can only probe this 3 by 3 block. So on top of the unitary mixing matrix U, we have extra non-unitary parameters alpha ij. And especially for these alpha 2, 1, it has a phase phi. This phi is a CP phase. And you can see it can change the mu2e oscillation probabilities, not just the delta t, but also this phi. And we can see if we include this non-unitary mixing, the chi-square would drop to almost zero if you don't have any prior knowledge about it. Then the CP sensitivity would completely disappear. And even for these typical HK. So accelerator experiment has no capability of distinguishing them. And we noticed that actually this would have a very interesting phenomenon. In principle, when the oscillation distance goes to zero, oscillation wouldn't happen. And then muon flavor neutrino would stay in the muon flavor. But for non-unitary mixing, we noticed actually the transition probability wouldn't vanish with these baseline lengths because it's a zero distance effect. And this is a very interesting thing. That means even with a very, very tiny baseline length from the source, actually we can see this signal. See this new E bar from the new mu bar. That's this red line. And it's very different from the background. Background has this shape. It comes from the mu minus decay at rest. And then we can just use one near detector, this is a mu near, with distance, for example, just 20 meters from the mu dot source. We can try to see whether there is signal or not. And use this to constrain the size of this non-unitary parameter, this alpha to 1. And we tune the background ratio and the detector size and to see what's the possible sensitivity at the future experiment. And it turns out it can improve the sensitivity to like a sub percentage level, for example, 0.5% something. And that is small enough because as I mentioned earlier, the CP effect is at a percentage level, several percent, 3%, for example. But if this alpha to 1 is less than 1%, then it wouldn't be a trouble. With this near detector, you can see first this 2K plus just mu SK. Still, the reduction is huge. But if we add this mu near, then it's almost no reduction. And also for this T2HK, the similar result. And the CP sensitivity can significantly enhance. So for this non-standing interaction, non-unitary mixing is not that big issue. And before ending this topic, I would like to mention non-unitary mixing is not an unusual thing. Actually, it's almost everywhere, especially for this seesaw mechanism. It's naturally introduced some mixing with between the active light neutrino and also heavy neutrinos. And it's up to the model. Sometimes the mixing can be large, especially the right kind neutrino needs not to be as the gutter scale, it could be low. So finally, I want to mention this running effect. Earlier, we know that non-standing interaction, non-unitary mixing, we know quite exactly how they connect with model, but sometimes the new physics appears not directly, they appears from this running effect. And this can also affect the CP measurement. So recently, we studied this effect on CP and how to say probe this running effect on CP. The basic idea is for this neutrino oscillation, what we need is first the evolution phase in the middle for those mass eigenstates. So everyone has an evolution phase. And for the amplitude, actually it needs two mixing matrix. One is for the production on the left-hand side of this figure. So it's produced from this charge current process, typically charge current process, because we need to know what's the flavor. We need to determine in experiment what's the initial flavor. Then we need to measure, or at least we need to know is some charged leptons. And then when we detect it, we also need to use some charged lepton for the detection. And it turns out these two processes need not to be the same. For example, the source, it could be just a pion decay. And then the momentum transfer cannot be that large. It's typically determined by the pion mass. But for the detection, it's the scattering with the nuclei. And then these two momentum transfer can be significantly different. For example, differ by at least one order. And then Q square would differ by 2 orders. And this difference actually can make these two mixing matrix different if there is Arch-Running. And we simulate earlier study just assumes that detection momentum transfer is a fixed value, but actually it's not. It has a wide span. And this would change the oscillation probability. For this oscillation probability, you can see it still has zero distance effect. Suppose there is, L is 0, then this exponential goes to just 1. And then this amplitude matrix is just a U times U dagger. If these two unitary matrices are the same, U times U dagger is just 1, the unit matrix. But if they're different, then it's no longer unit. You would have non-trivial transition. For example, this electron to electron or muon to electron. So just at the short baseline experiment, we can see this effect. So we are thinking that since this Arch-Running would, how to say, if there is Arch-Running, then in the CP measurement, there are 2 unknown parameters, at least 2. One is the CP phase, another one is the Arch-Running beta factor. And you can see if we include this beta factor, the CP sensitivity would be quite different. It becomes a contour. But if we have this near detector, we can detect this zero distance effect. Then we can combine the muon experiment with the accelerator experiment to exploit the interference from this Arch-Running and try to guarantee the CP sensitivity. For example, here the blue line is kind of like first the green line, the free beta. So it's just a free parameter. It has the lowest chi-square curve. But if we use this short baseline, then it can be improved to some extent. Of course, if it's fixed beta to 0, there is no Arch-Running. That's the highest one. But the reality is we need to introduce this CP if we are not so sure. So some new physics can somehow appear in this way. So this is also one thing we need to think for the CP measurement. So basically, that's the thing I want to talk about. For new physics, there are multiple new physics that can affect the CP measurement: non-standard interactions, non-unit mixing, and Arch-Running. Yeah, so that's the current status that I studied for this leptonic CP. Thanks.
Yeah, so yeah, thank you very much, Shao-Feng, for an interesting talk. So we have time for questions.
Yeah.
Who would like to go first? There is Yanis. Has his hand up.
Yeah, thanks a lot for the talk. I had a question on, I think, slide 24. You were showing the prospect, let's say, for, I mean, if you have non-standard interaction. My understanding, I mean, looking at these curves is like with these non-standard interactions, they only kind of affect the overall shape of the chi-squared, but do not shift the value, the sort of best fit value for delta. I would expect that if you have something that couples more to neutrino or to anti-neutrino, maybe you would also be able to shift. Is it just a specific choice here?
Yeah, thanks for the question. Here is just a solid data. I simulate the experiment. So we first import some file. We take this true CP to be -90, and then we generate the event distribution, those binned event distribution, and then try to fix it, fit it. Since it does not consider those fluctuations, so the best fit is always the same as the true value. Of course, in the realistic simulation, we need to allow those fluctuations. Then it would shift somehow. But that should not change the features that much. So we just use some ideal simulation.
Okay.
Thanks. Can I ask a follow-up question? Just if you go to the next slide, where you had, so 25, yeah. So there you discussed kind of how much it affects the so wait, maybe it's actually forgot which slides. No, so I think it was 24. It was actually that slide. So where you discussed of how much the NSI will destroy the sensitivity to the CP phase. What did you assume? How large were those NSIs? So those epsilons?
Yeah, actually, I didn't assume the value of it. So I just first when I do the simulation, I just use the how to say neutralization without NSI, without non-standard interaction to get
Okay.
those events. And then I try to fit allow switching on these NSI parameters and try to see what's the CP sensitivity. That's the thing I do. So the data need to have NSI, but in the fit, in the theory, I need to switch on the NSI.
Yes.
And
So but you switched then on that you set them to 1, or you set them only, or you varied them, you let them freely?
It's free parameters, free parameters. So at different points, it should have different best fit value.
So the NSI has a different best fit, but do you basically restrict the range for those, that they cannot be too large because there must be constraints on?
Let me see. I think in this port, I didn't limit it. I think. Let me see if I indicate it somewhere.
Yeah.
I think I didn't, but I remember in my paper I mentioned the allowed range at that time.
Okay. So there will be some. You basically made sure that it's consistent with what are other constraints on those NSIs, basically.
We should add this prior knowledge, of course.
Yeah. Okay.
But in global fit, actually, usually people don't publish this kind of version. There are 3 global fit groups for neutralizations. Usually people don't include NSI.
Yeah, that's right. They only take the standard picture and yeah.
So the current prior knowledge actually is the, how to say, some phonological info from data. So just one reference has some reference value, but not reliable, I would say.
Okay.
And for doing experiments, usually people don't use the global fit as input. Usually. So one experiment to fix it. For example, that's the experimental approach.
That's good. Yeah, thanks. There's, are there other questions? I have more. I want to give other people also a chance to ask. But if not, then I continue. So can you go to slide 26? There you had talked about scalar NSIs. So in principle, those scalar NSIs, so if it couples there to electrons, you could close the loop with the electrons and contribute to neutrino masses directly, right? That's
true. But the coupling is very tiny.
So the effect with that it basically just couples to that finite density of electrons dominates over the.
So you can see this effective Lagrangian is proportional to coupling square. This is for vector NSI, but it's the same thing for scalar NSI. It's y square. The overs is mediator mass square. So it's the same thing as standard interaction. Standard interaction is weak gauge coupling square over MW square.
Yeah.
And for this scalar NSI, typically it comes from very tiny coupling and very light mediator, because it needs to, how to say, satisfy other constraints.
Yeah. It cannot come from heavy new physics, because otherwise you get killed by charged lepton Flavor relation and so on.
Right. So for neutralization, it's very special. It's kind of like an effective operator without any momentum transfer. So Q square is exactly 0. So we can write on this. But in loop calculation, I guess we have this Q square, non-zero Q square, and sometimes it can be very large. So I'm not so sure how large effect it can induce.
Yeah. Okay, good. Yeah, no, that's I was just curious.
Yeah, thanks for your question.
Yeah. There's another question from Yanis.
Yeah, sorry. So I have a silly question about the, I mean, at the beginning when you're motivating a bit this experiment with stop muons, you were mentioning two advantages. One was like removing the degeneracy and then increasing the efficiency. So, I mean, I can imagine that the neutrino flux is larger, but since you kind of pushing now the energy to lower values like 45 MeV, because my impression was always that usually the neutrino cross section is kind of scaled with the energy. So if you have like lower energy for the neutrino, do you lose a lot I mean, is it more complicated to detect them or?
Sure, that would change the cross-section, of course, but at the same time, the baseline becomes much shorter. So if you look at the oscillation phase, it's something proportional to distance and inversely proportional to energy. So in order to roughly the same oscillation phase with a smaller energy, we need a shorter baseline. And that's the reason why for these experiments, typically the distance is between 10 kilometers to 30 kilometers in this range, 10 to 30. And for T2K experiment, I think I have some plot earlier. The distance is 300 kilometers. So the baseline is proportionally shorter. So if we compare the energy, 10 times lower. So baseline is also 10 times shorter. And with the shorter baseline, the dilution is much smaller because with a larger radius, the flux becomes smaller. So the number of particles per square meter, for example. So with the shorter baseline, the flux actually with exactly the same number of neutrinos, the flux at a shorter radius is much larger than the one at a longer radius. So this can compensate some. And in addition, we can produce more protons because this mu dot only needs 800 MeV proton, but for accelerator, it needs a very high energy. The neutrino is already kind of like a 500 MeV, and in order to produce that high energy neutrino, the proton should be much, much higher energy.
Okay, yeah, I see. Okay, that makes sense. Thanks a lot.
So finally, it's still okay.
Okay. That's great. So I see that we are over the time. So I would say we finished the official